Okay. Someone want to get the door? Since Wade is asleep, maybe Tripp could help him out. Okay. Yeah, we did 4-4 on Friday. Just kidding. We're skipping 4-4. So we're going to go right into 4-5. If you're wondering why we're skipping 4-4, we're actually going to do... There's two different ways to solve some of these equations in the unit. We're just going to focus on one of them. So 4-4 we're not going to need. Okay. So differential operators is the theme, and the goal is to use differential operators to write differential equations with them, and then use differential operators to actually annihilate or kill some stuff. So let's start with this. Dy dx, if we use the capital letter D, which is a differential operator, to stand for dy dx, and then we can say that capital D times y, I'm sorry, D would be d dx, then these two expressions would be the same. Okay, and the idea is that a differential operator transforms a differentiable function into a new function. For instance, if you have d applied to ae to the bx, this would become what? abe to the bx. Good. So we start with one function, and out comes another one. Okay, for this reason, we say that differential operators possess linearity, which means that if you were to apply a differential operator to a sum of functions like a f of x plus b g of x, that you're allowed to do what you think you should do, which is to apply d to both terms. And if that's the case, then we have a times d f of x plus b d g of x, where we're applying the differential operator to f of x and g of x, and a and b are just constants, so we wouldn't apply it to that. Okay. I think you guys get the idea there, but just in case, if we had d dx applied to dy dx, this would be what? If I wrote it with linear differential operators. D squared y over dx squared, which is essentially d squared y, right? Okay. So in other words, d to the n y dx to the n is d to the n y. D plus 3, d squared minus 4d. All expressions, all polynomials that have d in the as the variable can be considered linear differential operators. Okay, and the goal is that we're going to apply variations of these to differential equations. Okay, so first, so let's talk about applying these to differential equations. Any linear differential equation can be written in terms of d. For instance, if you have ay double prime plus by prime plus cy equals g of x, how could we write this using d? Let's do a d squared y. I think I know where you're headed, Buban. A d squared y plus b dy plus, and this is what you were headed at, right? So what would if I factor out the y, you'd get ad squared plus bd plus c. So then this would be the differential operator for this differential equation. Okay? And now, if we let L equal AD squared plus BD plus C, then we could also write the equation as L of Y equals G of X. So then we could say L is a second order differential operator since it equals AD squared plus BD plus C. Okay. I think that's pretty much all the background we need. Let's just do one example. If we have y double prime plus y prime plus y equals 3x, if I wrote it in differential operator format, what would the left-hand side be? Let's just use D. Times the quantity of y equals 3x. Okay. Last remark. An nth order differential operator factors as long as the auxiliary equations factors. I think that's pretty clear. The auxiliary equation here is m squared plus m plus 1, which is essentially the same thing, just using differential operators. Okay. Are there questions before we move forward? Okay, so this brings us to the annihilator. And the idea is that if L is a linear differential operator such that when we apply L to some function y, we get 0, we say that L is an annihilator of y, or that L annihilates y. Sounds pretty violent, but it will be somewhat useful. So for instance, if we have D applied to any constant, that would give us what? 0, good. if I wanted to annihilate x, what would I need to apply to it? D squared. Apply d once, you get a constant. Apply d again, you get 0, right? If I have x squared, or for that matter, any quadratic, I would need d cubed. This one's pretty easy to see. So we say d to the n annihilates any constant x squared, all the way up through what power of x? X to the n minus 1. Good. So, therefore, to annihilate a polynomial of degree n, I'm sorry, not degree n, degree n minus 1, you'd have to use d to the n. Quick example. To annihilate, let's say, 6x to the 5th minus 40x to the 4 plus 31x. What do you use? These homework problems are going to take you like a second, just so you guys know.
Yep.
Eddie still doesn't believe me. Okay. For the most part. I mean, there's three families that we have to learn. So we know how to annihilate polynomials now. Okay? Yes, we know how to kill polynomials. Not examples, sorry. We also need to talk about exponentials. So if we're talking about e to the alpha x, x e to the alpha x, think of the family of solutions where we have e to the mx, but then we may or may not have repeated roots, right? What happens if I repeat the roots? This x becomes x squared, and so on and so forth. Okay, so to annihilate all this stuff, so in general, if we want to annihilate this, which would in turn annihilate any of the ones preceding that, we would use d minus alpha to the n. So think, if there's no x in front of it, that means that it was just a single root, right? And if there is an x in front of it, that means that it was a repeated root twice. So then it would be d minus alpha squared. And if you see x to the 11, that means you got to use d to the 12, or d minus alpha to the 12. Okay?
Can you show how that works?
You will show how it works.
Okay.
So let's say we have e to the 6x. What do we use to annihilate that? So we're going to use d minus 6. And if you're not sure why that works, let's apply that to e to the 6x. So if I apply d minus 6 times e to the 6x, when you apply, well, you know what? I'm not going to skip any steps. Just distribute like you think you should, right? So this becomes d e to the 6x minus 6e to the 6x. And then what do we do from here? the derivative of e to the 6x is, and when all is said and done, you get 0. One more. You guys try this one and verify it. If you have 4e to the 3x plus 2x e to the 3x, what do you use? And then verify real quick that that is indeed the annihilator of this expression. So besides Roma, who's absent? What annihilator are we using here? Squared, right? Y squared? Think e to the 3x has been repeated twice, right? Because you have some x in front of the second one. So if you use that, d minus 3 squared applied to 4e to the 3x plus 2x e to the 3x. What do we get? D squared minus 6d plus 9 applied to 4e to the 3x plus 2x e to the 3x. So now I'll take d squared, apply it to both. D squared applied to 4e to the 3x, and then d squared applied to 2x e to the 3x. Minus 6d, apply that to 4e to the 3x, and 2x e to the 3x, and then plus 9. Well, here, let's just combine it. What is that? 36 plus 18. So that's just going to be 50. Well, no, I can't combine that. Never mind. So 36 e to the 3x plus 18x e to the 3x. All right, so when we apply the derivative to 4e to the 3x twice, what is that? 36 e to the 3x plus, and you know what? Let me, in between this line and this line, let's do the derivative of this once. So then that would be, with the product rule, 2e to the 3x plus 6x e to the 3x. And then we apply the derivative again, so that gives us 6e to the 3x for the first function. Second function, we need to apply the product rule again, so that's 6e to the 3x plus 18x e to the 3x. Let's see, where are we at? Minus 60, that's going to be minus 24. And then do the derivative once. What do we get? That should be minus 72 e to the 3x minus 6d. So we're going to have minus 12 e to the 3x, and then minus, with the product rule, minus 12 and 3 is 36x e to the 3x. And then we have everything else, plus 36 e to the 3x, plus 18x e to the 3x. If I did everything right, it all should equal 0. So here's 18x, 18x, these cancel. 36 e to the 3x, 36 e to the 3x, and minus 72 e to the 3x cancel. Then we have minus 12, and then plus 12. All right. So some of these can be kind of pesky to verify, but to actually annihilate, once you guys get out of this section, you'll be using these to solve differential equations. You're not going to have to verify it. You just know that it's going to work, and it saves you some time. So the last kind that we need to worry about are basically kind of like the third scenario we talked about yesterday, or on Friday. If we have e to the alpha x cosine beta x paired up with e to the alpha x sine beta x, and of course if we repeat, then we'd have an x thrown in front of each of these. I'm kind of separating this because, for example, here we would use the operator we're going to talk about to a power of 1. Here we would use the operator applied to a power of 2, and so on and so forth. This would be x to the n minus 1, e to the alpha x, cosine beta x, x to the n minus 1, e to the alpha x, sine beta x. If you see just a cosine, e to the alpha x, or just a cosine, it's going to be the same thing that you would use if you saw both of these terms. Okay, and vice versa. Like if you saw the sine and not a cosine, you'd still have to use it. Okay, so, and what you end up using is d squared minus 2 alpha d plus the quantity alpha squared plus beta squared. So that you're just going to have to remember. And then whatever amount of repetitions there are, so here there's no repetition, here there's a repeated root twice, here there'd be a repeated root n times. So then this expression would annihilate everything that I just wrote. Okay? Now obviously you would only use whatever you need. So for instance, if we had e to the minus x cosine 2x plus e to the minus x sine 2x. Easiest thing to do is to identify what alpha and beta are, so then you can just use the formula. So here, what's alpha? And then beta. So we would have to use d squared. And then what?
Plus 2.
D plus, and now we just do the sum of the squares, so 5. So if we use d squared plus 2d plus 5, that will annihilate these two functions. And if these were repeated, if we had like an x squared in front of each of these, we would just make this to the third power. Does that make sense? Okay. What else should we say? Last thing, and then we're done. The product of annihilators, let's say L1, L2, and so on, will annihilate the sum of functions. So like y equals c1, y1 plus c2, y2, and so on. So if I had, for example, if y1 was some exponential function, and then y2 I realized was just a regular polynomial, to annihilate this whole sum, you would just take the product of the annihilators, okay, and apply that. So for example, this will be the last. Well, we'll do two of them. If I have 7 minus x plus 6 sine 3x, how many types of functions do you see here out of the 3 that we've talked about? 2. This one you can group together and use what to annihilate that? Which would give us d squared. And then here we have another family. This is easier because we don't have the exponential attached to the front. What do we use here if all we have is beta? D squared plus 9. So then to annihilate for the whole expression, so for the whole sum, you would use the product d squared times d squared plus 9. Try one more. E to the minus 5x plus 6x squared minus 5 plus x e to the x. Let's go straight to the answer here. How many families of functions do you see? Well, 2, but yeah, these are actually going to be different annihilators. So there's 2 types, but between those 2, one of those you have to do separate annihilators, right? So what do we use for the first term? D plus 5 multiplied with d minus 1 squared. Good. Questions? All right, we're done. Go annihilate some stuff, and I'll see you tomorrow.